I was asked for the title like last year, I suggested versatile language conditioned robots, right? So that was the title, and then Svetlana asked me a couple of weeks ago, hey Rudy, do you want to update the title? And I was like, yeah, sure, give me like a day to think about it. And I think like 5 hours later, there was a Slack post with the title, so you decided for me, I guess. But the rebel that I am, I decided to modify it slightly. So what I want to talk about today is learning versatile language conditioned robots behavior efficiently, right? And the efficiently part is highlighted here for a reason, and you will hopefully see a reoccurring theme, right? Like where we try to be a bit more efficient than what's out there right now, and hopefully agree with me that this is exciting and interesting work still within this domain that is very data-driven these days, right? So, big picture, we all that are in the robot learning domain, right, that we kind of envision a future, something close to this, right, where we have autonomous agents doing chores at home, like cooking for us, or vacuum cleaning, right, or just cleaning up. And a big promise back in the, or still is, in order to achieve this, imitation learning, right? So simply for the reason that pre-programming all of this behavior is nonsensical. So if people were saying you know what, as long as the human can do it and we can observe the human and how they're doing it, we can basically transfer this to a robot, right? And that sounds super exciting and great. But then the sad reality, right, of university basements worldwide is that we then stand there and we show each skill individually. At least that was back 2017, right, when I did my PhD still. And that was actually the third hand project where Mark was a part of, right? So anyway, so here, basically, I had to represent each skill to the robot individually. And that annoyed me quite a bit, right? Because it shouldn't be that cumbersome. So what we did back then is that we decided, okay, we're actually going to demonstrate the entire task at once and let the robot figure out which skills to learn, right? So at this point, we were basically able to give 6 demonstrations of the entire task, and the skills were then learned autonomously through a method called probabilistic segmentation. But if you now look again what this looks like, the human demonstrations are very, let's say, robot-like, very artificial, and so on, and this is still just one task. So if you consider how many tasks you actually want the robot to solve at home, that is still very annoying and unsatisfactory, right? So the first question that we're going to address today is how can robots actually learn versatile behavior efficiently, right? And for in terms of nomenclature a little bit to clarify things, versatility in this case actually talks about multimodality in the behavior space. Because now when we talk about multiple policies and everything, it could be multimodality in the input space, right? Or multimodality in the output space. So we converge to the definition multimodal means input, versatile means output, right? And efficiently here in this case would be with respect to the human demonstration effort. So how can we minimize the work that the human has to do, right? In order to demonstrate a versatile set of tasks, or in order to learn from a versatile set of tasks without having to demonstrate each task individually. So, and if we look at other fields related to robot learning, right? So we noticed recent trends which went in the direction that we actually need diverse data to do so, right? So for instance, with current models and the last couple of years, LLM models like Claude or ChatGPT and text data, they learned on a very diverse corpus of language, right, of text. The same images, the images are trained on very diverse set of in the wild images and so on, and are able to generate these amazing new samples, right? And the generation process for language or image isn't that much different than the generation process for actual behavior. There's of course differences, but both are generative models if you want, right? So what we were thinking, okay, so how about actually also doing the same thing and just basically trying to learn from a very diverse set of data, right? So in the lecture, usually when I talk about this, I gave this example of back in the day, we tried to go from A to B and demonstrated a bunch of times how we actually did this, right? How we, for instance, would navigate there, and then we have our distribution around, or the expert state distribution together. And in play data, this would look more like this, right? So we basically have fewer samples that do exactly the same path, but they instead cover the entire action space or state space. That's at least the hope, right? So now the question is, how can we actually learn from something on the right-hand side, right? So the benefit here is clearly that this task agnostic or play data, right, is like cheap and allows us to scale much faster with demonstrations, right? But it also has downsides. And this was, I should mention, first introduced by Corey Lynch in the work Latent Plans from Play, or Learning Latent Plans from Play at Call 20. Yes. So again, like, it works really well in diverse multitask settings. Data is cheap to get and easy to collect because you don't need to worry about resetting the stage or anything like this, right? And policies generally like perform better in case of, for instance, like things go wrong, or like since you have like recovery examples usually in your data set, right? However, nothing in life is free. So in order to be able to learn from such data, we need policy representations that can deal with the underlying multimodality, right? So, or intrinsic multimodality of this type of data, right? It needs to scale well because we now have like huge like data, amounts of data suddenly, right? And usually the demonstrations that we have or the policies that we observe are much more complex than a simple Gaussian, right? So we need to somehow also be able to model this very expressive underlying distributions. And if you look at the types of like policy representations that are out there, right? So starting with like just some linear representations, they might scale well with data and they might even train stably, but they're not really very expressive or can deal with the multimodality, right? Then GMMs have been for a while like super exciting. The initial work that I showed, we also solved this with GMMs, right? They have, of course, the multimodality. I would even argue to a certain degree they're also expressive, but in terms of scaling, it becomes much more problematic in order to basically get them working on large data sets, right? Then like a whole area that tries to basically discretize the action space and use technologies that we know from language modeling or vision, like transformers and so on. Also, it's fairly successful, right? So there's like behavior transformers and so on. All of this works really, really nice, but the underlying distribution that they actually learn is, I would argue, not super expressive. Not super expressive. And then finally, we have energy-based models, which had like a little bit of a like hype moment, and everybody was super excited about them until people started to actually try to get them to work. And they train very unstable and are very hard to get to work nicely, right? So still, I think like aggressive work, great and everything, but we want something easier to train, right? So we argue that we need better policy representations that are expressive, multimodal, and scale well with data and also the action spaces that they're supposed to produce. So back in 23, we suggested hence BESO, which we argue checks all the boxes. It's expressive, can deal with multimodality, scales very well, and it trains incredibly stable. Okay. So we presented this work at RSS 23, and I'm going to talk a little bit about this now. So the idea of BESO in general is to use diffusion models, and chances are that you by now already heard about diffusion policies quite a bit, right? And most of the diffusion work that is out there is actually based on this work, denoising diffusion probabilistic models, which is great, right? And however, the representation here would be, well, you could describe it basically as hierarchical VAEs with like not lower dimensional latent spaces and a priori known encoder, right? So that's great. And there's also like very famous work from Shoran Song's lab, Cheng Chi, did like amazing work together with TRI, where they showed that a policy or behavior based on such a DDPM-based diffusion policy can achieve really impressive results in terms of multimodal and variable tasks. Show you the clip again. Right, you can see like very diverse task sets here and like learn all of this behavior very, very nicely. However, there's also like a different perspective on diffusion, which I personally favor, and that would be looking at it in terms of score fields or SDEs, stochastic differential equations. So here the idea is that we can actually describe a diffusion process, right? So the process from structured data to unstructured data, or from structure to noise, right? As a stochastic differential equation where we basically have dW as the Wiener process, or the Brownian motion if you want, right? And then fxt would basically be the drift term. And what we do is here, basically at any point in time, right? Time here meaning the actual noising process, right? We can add a varying amount of Gaussian noise, and that would lead us from something like a very structured distribution to just like a pseudo-Gaussian distribution. And there's this impressive work by Anderson, well, I think this was actually just him, not at all, in 1982, where Anderson showed that for every forward SDE in a diffusion process, there's also a reverse SDE, which sounds like black magic, but it's just math. It's math and it's beautiful, and I like it a lot. So the idea here is basically that you can actually describe the way back from noise to structure also as an SDE, right? Which sounds crazy, but the math works. And the only thing that, or the one problematic thing here is basically that you need to know this term. Is there a laser pointer? Oh, yeah. You need to know basically this term, which we call the score function, which is the gradient of the log of the marginal probability at any time step, right, of the image. Again, time step here meaning in terms of the noise process. And that thing usually is not analytically solvable and usually is not known a priori and so on. So like you need to approximate that somehow, right? However, if you actually have like very strong function approximators, right, like something that can learn potentially universal functions, right, then, and enough data, you could try to learn this. And this is exactly what diffusion models do, right? Like with our current deep learning models, we're actually able to approximate this function quite well. At least well enough that it's useful. And this is literally what diffusion models learn. Right, so the path that we're going, or in my lab that we're following, is following Karlsruher et al. And this is based on the paper elucidating the design space or of diffusion models, or short, usually in the literature you find it as EDM, right? And that one is a very modular reformulation of this score-based diffusion process, which has a lot of hyperparameters that you can choose. But most of them actually work really well if you just fix them to some like value that you can heuristically define and or like come up with, and it works actually quite well out of the box. So yeah. So what do score-based models actually look like in terms of illustrations, right? So the idea is that if you have some underlying distribution which is complex and you don't know it, right? Like for instance, you have like some images of dogs. And then you can use this forward SDE, or like the forward SDE would describe what this would look like in a latent space that is basically just like random noise or Gaussian distributed, right? The only issue is that we cannot create samples in this space. However, we know how to create samples in the Gaussian space, right? There's nothing easier than that. So we can create a new sample in the Gaussian distribution, and then after learning our score function, we can basically sample like the next action, right, iteratively, like at every time step, and generate basically the denoise sample that hopefully is drawn from the same distribution that we had originally underlying, right? So that's the idea. And since we can do this for images, we can also do this for behavior, right? So the idea is that at the beginning we have structured behavior, so like some trajectory that we're actually following, and then the behavior is somewhere like all over the space. Like imagine that each dot is a different point in time, right, of your trajectory, and that is of course like jumping around like super noisy, very like problematic. And here we have again a denoise sample, which is actually again smooth and corresponds to the underlying complex data or behavior that we've observed in our demonstrations, in our latent plan. And as you can see here already, just from this image or from this illustration, we have a multimodal distribution that we're learning, right? So if we actually have like, or without actually defining how many modes we have here, right? So we actually just learn something very, very expressive, or how to get from something simple to something very expressive, which is exactly what we wanted in terms of learning from play data. So question could be now, what does our forward or reverse SDA actually look like? A little bit of math for you, right? So again, if we basically have this kind of like illustration that we go from something structured to something unstructured and something structured again, we follow, as I mentioned, the EDM formulation. So our forward SDE would basically look a lot like this. So our F term, as we had in the previous slides, would be the entire first part here, and then this part here would be our noise injection term. So we have the drift term F, and we have our noise injection D. And the reason why this was chosen this way, right, is for a variety of reasons, but like the nice thing is that if we, for this SDE, actually want to define the reverse SDE, it's nothing else but adding a minus sign in front of the beta here. And that's what makes it really, really like like adds a bunch of nice features. And in practice, here comes the next thing, right? In practice, we chose sigma t as t, which means that the derivative becomes 1, right? And we have like every derivative as sigma t, it's replaced by t, so the whole formula becomes much, much simpler. And it becomes even simpler because at the end of the day, we actually only care about this first part, or actually what we care about is the probability flow ODE, but I will talk about this in a second. So now the score function, the one that we actually learn, we parameterize as the difference between some function output, d, right? Or the difference between some function output and our like action at that time divided by sigma squared, right? And the reason why we choose this formulation is because basically the objective afterwards becomes super, super simple because of this. Our d function looks again very complicated, but the only thing that you really have to keep in mind here is that f is just some neural network. Can be a transformer, can be like an MLP if you really want to, right? But it's some kind of like model, and all of those constants, or not constants, but all of those coefficients, right? They basically modulate the skip connection, and they make sure that the input variance is normalized and the output variance is normalized at any point, right? So that makes basically just the learning much more stable. And then the reason why we basically chose D the way we did is that our objective now simply becomes an MSE loss between our D function and our initial data point that we had in our data set, right? And in order, if you're actually interested in deriving it yourself, I highly recommend this work here by Pascal Vincent. It's just a technical paper, I believe. I don't actually think it's published anywhere, but it's really nice to follow, and it's good work. So I encourage you to have a look at that one. And the second part is, as I mentioned, we actually only care about this little thing here and not this whole reverse SDE, because this so-called probability flow ODE has the same marginal distribution as the reverse SDE, right? Meaning that if I draw infinite many samples, we end up at the same distribution. So we can ignore the actual noise injection term. And again, furthermore, if you again consider that we replace sigma t by t, then it's just like -1, this difference t, and that's what we then use, for instance, in like an Euler equation or whatever in order to get to our next action. Okay, so with this in mind, we know like all the parameterization of our SDE, and now the next question becomes, where do we even get these samples to begin with, right? And that brings us back to the play data. If at any point I go too fast, let me know, right? But what's that like? I mean, as I said, you don't need to know this by heart, but I think it's good to have at least seen once instead of always hearing like diffusion turns noise into structure like black magic. No, that's actually, there's math behind it. Have a look at it. Anyway, so where do we get these data points in the first place, right? So as I mentioned, we're gonna work on play data, right? So we have some trajectory of some robot doing something, right? And we can assume that we have a sequence of state actions, right, over several times, and but they don't cover the entire trajectory. So there will be somewhere a point in the future, right? And we know, like, if we follow, like, or we know that like these state action sequences that we observed can potentially, right, lead us to that goal, right? So we basically can take this as a data point that we say like our data points that we, or our distribution that we're trying to learn, the underlying play data, is given as the actions given the state and a given goal, where the given goal can be something manually defined, but it can also just be some future state, right? And with this in mind, we basically structure our entire data set always like this. We basically just take like some point in the future, define this as the goal, and take the current sequence of like P steps as the current state actions. Yeah, and this looks exactly like the stochastic differential equation that I just showed you, right? So we have basically our skip connections and our coefficients, and F is basically our, in this case, a transformer that we choose where we input the noise, the current states, right, or state action sequence, the goal that we want to like have our behavior to approach, right, and our current iteration of our action. And what we get out is the next iteration, the slightly denoised action, right? And as you can see, like this is happening in a loop, right? So we basically do this n times, right? And those are the so-called denoising steps. So we do this basically however many times we need in order to get from something completely like pseudo-Gaussian to an action that we can actually leverage and we can use. And the beauty of this whole structure here is that we can very straightforwardly extend it to produce entire sequences of actions. Instead of just giving you the action of the next state, we can have like a sequence and then do like action chunking or anything like this in order to make sure that like our behavior is actually more efficient or smoother, so we can predict directly multiple actions into the future at once, right? So yeah, so this all is Basel. And to back up our claims, we of course did a lot of investigation. So the first thing is multimodality. We actually, and I will talk about this in a second, we created a new benchmark, D3IL, where we actually where we actually analyze models for their multimodality. So we measure the actual entropy of the behavior and so on, and while also measuring the performance. And one of the most visual toy tasks here is just avoiding all of these obstacles, basically going from left to behind the green line, right? And as you can imagine, there's like a variety of ways of doing this. And this would be the illustration of the trajectory or some rollouts of Basel. And you can see that we actually maintain like multimodality, so we don't always do exactly the same thing. So in terms of scaling and expressiveness, we evaluated this on a bunch of benchmarks that are out there and performed or sort of behavior out of it. So I think like we can just make a check mark there. Just some results. Again, like I encourage you to have a look at the paper if you're more interested about this. Yeah, and again, it scales like really well with data and better than like just plain or naive goal conditioned behavior cloning and CBED or even Hulk, right? Which back then was the state of the art on the Kelvin benchmark.
So can I actually
sure.
ask questions? So the whole thing of goal conditioning is anyway a big question, but completely in this experiment, what are the goals?
Language goals. So you get like you get told do X or put the yellow block on the green block, and then your behavior has to be that. Kelvin is one of the benchmark, or if not the benchmark, mostly used for this, or actually like even designed for this, right? Because you provide or you have language labels for each demonstrations. But in this case, even you can just use the future state. So I think in this one, we actually didn't use the language one yet, but just a state where we, which was like denoted as the pink block was on the orange block or something like this. And you can basically try to achieve that state.
You automatically annotated this final state to be the goal for the like play demonstration, right?
Or for rollout, yes.
But in the language case, it's not really like a goal in the sense that you could test it. So it's just a language conditional, right?
Yeah. So it's like it's a language conditional, but like ideally it corresponds. I will actually talk about this in a second, where we used this desire that we want to have like our goal representation, which is, for instance, in the same representation as our state, right? And a language orientation being aligned, right? And then this way. We were actually able to achieve like performance, but yeah, just okay. Okay. So something that I haven't talked about yet, but which is really, really nice and falls out of the score-based formulation here, is the compositionality of score-based diffusion models. So in our case, for instance, what we showed was that we could train a goal-dependent score, right? Like where we always have like the goal state as an additional conditional. Additional conditional in our score function, right? But in 10% of the time, we used a like predefined non-goal token, basically just telling our transformer like there is no goal, right? There's no goal, and like but seeing the same states and actions as a data point with the goal, right? So we basically just replaced it. So and this allows us to simultaneously or to also train a goal-independent score. And the beauty here now is that we can actually, during runtime, so like without any retraining, combine those two. So we have a waiting term, lambda, and depending on how we choose lambda, we will follow the goal, or we will be more explorative and like ignore the goal and just do something, right? Like this, that we're supposed to do in that state, or one of the options that we have in the state. And for instance, on this like illustrative toy task, where we can see this very clearly, that with like an increasing lambda, we're following only or we're shifting the gradient field to follow only the desired goal, being that modality here, right? And if we actually shift lambda towards 0, we are becoming more explorative and like have our denoised actions going in either of those two modes, right? And that's really, really nice. So this way we basically can learn goal-dependent, independent policy at the same time. And as I said, we can do this during runtime. So let's say, for instance, you like imagine your agent does something and you tell like the agent to pick up the glass of water, and then the glass of water suddenly disappears, right? So you can directly turn while execution, you can turn off the goal following and like be more explorative to see where the glass is actually, right? And there has been this idea of compositionality has been picked up on follow-up, like really interesting follow-up work. Two noteworthy ones are POCO here, in this case, where they actually do this more in the data space. And this one, Nomad, which like some colleagues from Berkeley basically used this compositionality or build up on score-based compositionality, as we suggested, to do navigation tasks. So basically, if the agent can see their goal, right, or its goal, it will follow like a goal condition policy, and if it's unsure, it will follow more or navigate more in an explorative way. Yeah, and that one actually got best paper award at ICRA, I should mention. So like people seem to like the idea. So now you must be asking, what's the downside? You talked at length about this, so there must be a price to pay, right? So usually, like people always bring up the issue that diffusion policies have this multiple inference steps, right? As I said, like we basically sample an action, denoise it, use that one again iteratively until we end up in our desired underlying policy or like distribution space, right? And usually, like with DDPM-based approaches, at least back in 23, like they were performing 50 to 100 denoising steps, right? Again, the really cool thing about score-based diffusion that we showed is that we were able to outperform all of our competitors on various benchmarks with only 3 to 5 denoising steps, making us 10 times faster, right? So that is like that was really a really nice result. Yeah. So if you think this is cool and interesting, like RSS23, there's code available, there's the paper available, and so on. So feel free to take a picture or. Okay, so we showed that basically Bezo achieves SOTA goal conditioning, goal conditioned behavior with only 3 denoising steps. So back to multimodality. I mentioned that we have like this new benchmark, and the question is, why did we even like come up with this new benchmark? And that is that in all of these methods claim multimodality, right? Like even like behavior transformer and others, they say like, oh, we learn expressive multimodal behavior. But if you actually look at the evaluation, there's no benchmark out there there was no benchmark out there that was dedicated to evaluating the multimodal behavior of these models, right? So there were like several benchmarks for like all kind of things like long horizon tasks, task complexity, like dynamic environments, like changing environments, like Colosseum and so on, right? All kind of, okay, cool. All kind of like issues, but there was none specifically for multimodal behavior or probabilistic behavior. So we introduced D3IL, and the idea there is that we don't only look at each state individually, right? But we rather look at the entire like trajectory, entire behavior, and define a priori different key states or key points that we say, okay, if this was followed or that one followed, like this is solving the same task but in different modes, right? And then we can measure the behavior level multimodality or entropy here, and we can say like, okay, if a policy actually does the same task with the same prompting, like in different ways, then it maintains multimodality. And the different ways is basically what we measure through our defined key states or key properties, beta here, for instance. So this could, for instance, be in this task, which of those 2 blocks do we actually push first, the red one or the green one, right? This is something very easy that we can see, right? And that we can measure. And the question is if you have a multimodal behavior, it would ideally vary between them, right? Because we did pay attention in the data generation that is the underlying in the policy learning that both these cases happen equally frequently, right? So on these kind of things. And however, if your policy just converges to one of those 2 solutions, you will always push the red one first and then the green one, right? Does it make sense? Okay. and we had like 7 different tasks. And I think just as an illustration, some of our SOTA competitors are not actually that multimodal as they claim they are, right? And however, Bezo is really nice and it's high entropy, as we've seen in the previous plot already. Yes, and this was published at ICLR last year, and people actually are picking up at it and using quite a bit. So I would argue, if you claim that you have versatile behavior, prove it, right? Like, show us your performance on D3IL, right? We collected, by the way, a total of 8,790 actual human demonstrations. So that is also something to keep in mind, even if you don't care about multimodality, but you care about learning from humans, that could also be interesting for you. So now hopefully you all agree diffusion policies are great, right? But diffusion policies on real robots often suffer from low control frequencies and jerky movements, right? So the next question will be, how can we make the behavior generation more efficient and smooth? And efficient here with respect to the inference time, but also to the control frequency. And just like very briefly mentioned, because I heard that you do surgical or like medical applications now, not medical robotics, but here's something that we did in the domain of surgical robotics or medical robotics, is that we combined Bezo or like score-based diffusion with our primitive representation that we introduced earlier, so-called pro-DMPs. And instead of producing directly actions for the robot, we're producing the weights of the primitive. We still denoise the resulting trajectory and not directly the weights themselves, but that results actually in much smoother and more gentle trajectories with respect to textiles and like deformable objects and vulnerable objects. And that was also published at RAL. So just some example. Oh, does it not play? It doesn't. Let me try this. Oh, yeah. So for instance, left you see like diffusion, even like a smooth diffusion variant, and on the right-hand side you see what the MPDs do. Movement primitive diffusion, I should say. And you can, I hope you agree that, like, if this would be some internal tissue, I would prefer the right hand. No, but that's the way to go. And we did this, or we evaluated this on several tasks in the SOFA benchmark environment, but also on proxies. On this is basically real robot tasks, right? This is not simulated on proxies that behave similar to actual tissue. And this was worked together with Paul Scheichel and Franziska Mattes-Ulrich from VU Erlangen. Yes. So combining DMPs with movement primitives actually yields very gentile and accurate and fast behavior. So you might still argue, well, okay, fine, but we still need multiple inference steps, right? So furthermore, improving the behavior after the policy was learned is non-trivial. So reinforcement learning with diffusion, there's some work coming out now, but generally in diffusion you don't have tractable likelihoods. So out of the box reinforcement learning methods that we have and that we know and that we like are not easily deployable to previously diffusion-based behavior, right? So how can we execute, so Q4 would be how can we execute and refine diffusion policies more efficiently? And here again, efficient with respect to the inference time, but also with the further improvement. So what would be the next steps? And here I cut down a couple slides, so we're basically just going to illustrate it here. But usually here you have the same diffusion process as before, in this case actually the reverse diffusion process or denoising process, right? So we have some, the desired actual behavior, and then we have like just the noisy behavior. And diffusion processes are great because they train very stably, right? But the inference is slow and we don't have tractable likelihoods, just to reiterate what I just said. However, back in the day, we used mixture of experts, which for multimodality, as I initially mentioned, right? However, while they have tractable likelihood and are very fast in inference, they are usually not very easy or very nice to train, right? So like there's several things that you have to consider, and it's always problematic, and there's like a ton of literature on how to do this efficiently, right? So, but what we were thinking, if we actually have already behavior, so you give us your diffusion policy, right? And we're just gonna, we're not gonna tune this anymore, we're not gonna touch it anymore except creating like some rollouts or using it for inference, right? And we have some initial states. We're basically gonna see, or we're gonna analyze, or distill the underlying multimodal behavior out of it. And we're going to use variational inference for this, right? Because we can show that with like some representation tricks, we can actually use the score function instead of the probability of the policy directly. Yes, so illustrated, this would, like this again, like an illustrative example that we did. The purple background here corresponds to the actual vector field, and we just highlighted the local optima here, right? So we have several ones, and here all started in the center, but they don't have to, right? So, and through this like iterative variational inference process, we push the individual components, like the orange strings being the components of our Gaussian, closer and closer to the local optima until they get stuck there, right? And we, so if we have our mixture model, what does this look like in terms of architecture? We have our gating category, or like a categorical distribution, which chooses which expert to sample from, right? And we have the individual experts here as different heads. So this now represents like a multimodal distribution, where more experts equally increases the expressiveness of the underlying distribution, which is really nice. We have tractable likelihoods now that we can leverage in like common RL methods or well-known RL methods, right? And we have fast inference because we can do this all now basically in one pass-through the transformer instead of having to do this iteratively, right? So this is in our work, this is the exact same architecture as the underlying diffusion process, right? Because we didn't want to change anything that results in, I don't know, some artifacts basically that would make it work. No, this is exactly the same architecture, just that we basically replace the heads with like experts. And yeah, that works even with transformers. So just to give you some idea in terms of like milliseconds, right? And the functional evaluations that we had to do. And in the paper, we also show like our performance compared to our competitors and like to other distillation approaches and so on. Yeah.
Do you have to know beforehand the number of modes?
In this version, yes. However, we already have like some follow-up work where this is basically where we can show that we can make this even more efficient and just go either of two ways. We can basically just always add additional experts during inference, not during inference, during the training process, or subtract them. But yeah, that like with the newest version or the follow-up version, we don't use anymore.
On an implementation level, do you use the state encoder that you trained for the diffusion model for the downstream model, or do you retrain like the full thing?
I'm pretty sure that I think we tried both, and I think like the one we stuck with is like we keep using it.
Other question. So EM, like the classical EM, has local optima, right? Mm-hmm. Does this in principle also have local optima? And is this an issue?
Well, since we're using the reverse, like the local optima, so I would argue, given that we use here the reverse call and we're more mode seeking, so like if you if your vector field has local optima, you might get stuck in the local optima of your vector field. But overall, you won't have any issues like mode averaging and getting stuck because of that issue, right? Because that's usually what happens in EM if you have the wrong number of experts, right? So what could happen instead, the only downside is that you might not have enough experts and hence ignore some of the optima, right? But you shouldn't have like this issue that you get stuck somewhere in between because you're jumping between two equally important modes.
And why not here?
Because the experts themselves also like basically push themselves each other apart also, right? So you would maybe you can construct like an issue if all three of them, like if you have two. I think there you could construct maybe something, but in practice, like I don't think that's an issue.
Doesn't it depend on the initialization?
Well, that also, right? But like usually, like again, like yeah. So I don't think like because of the choice to use the reverse call, I don't think we're that affected by the initialization terms either. Right? But of course, like if you initialize next to like very steep local optima, then you might get stuck, right? But yeah, in practice, you're trying to get these issues in particular. So just to give you an idea, so in the training, basically, we still have like our M steps and E steps, and then during inference time, we have our gating, which chooses which expert to sample from, right? And then the expert produces the action that we then perform. And this is happening based on the actually previously learned diffusion policy. Again, And it doesn't have to be a score-based diffusion policy. We actually can do this also for DDPM-based policies without any issues. Yes. And we can even do this for flow matching too, but that's a whole discussion if this is even still interesting for flow matching or not. We can have that all the time. Complain about this now. But yes, theoretically, you can directly deploy this to flow matching methods. Yeah. As I mentioned, SOTA performance all over the board. Yeah. Again, if the, and one thing that I didn't mention, since we now have actually explicit modes, we can actually look at what the modes do, right? So, and again, in our like favorite obstacle avoidance task here, the really cool thing that we can do is basically to see what the trajectories or which mode was active, which expert was active during any part of any trajectory, right? To see like, oh, which expert feels responsible for performing which actions. So basically opening the door for some kind of interpretability, right? And we can even, so like see in this task, right? So if you choose 8 experts, which might be too many, right? Because this and this expert, I don't think we actually would have needed it. Same as here, this one would most likely be subsumed by some of them. But given that we chose 8 experts and they basically split up the space between them, this is what we can see and interpret here. And the nice thing is, if we actually don't want the robot to perform any of these type of actions anymore, we can basically just block the expert and say like, don't sample actions from these experts, right? So then the robot will not do anything remotely or anything related to this expert, right? So again, this was published or presented a couple of weeks ago in Vancouver. Yeah, and we can basically have tractable likelihoods with one-step inference and still perform SOTA behavior. So again, all of this is great. Back to the goal-conditioned stuff, right? So because we want to talk about language, because I heard like you all are excited about the language part of this talk, right? And I would argue language is the most intuitive way to communicate goals, right? And we talk about versatility and goal-conditioned behavior and so on. And now we kind of want to use language for that, right? So how would we do this? So like we could just use data, right? And say like, oh, we have like Calvin, for instance, right, with language annotated data. But the problem is that actually, if you look at the data sets, at the available data sets, well, now with Droid, it's slightly different. Well, it's not actually that different. Droid is a huge data set with a lot of language, right? But with actual language annotations. But back when we presented this, the following work, we had like roughly, I think only 10% of the data in any data set was language annotated. So that is like a huge pain. So the question is, how can we actually learn language conditioned behavior efficiently? And here efficiently means with respect to the amount of available language annotations, right? So if we now again have, for instance, our data set, or actually let's start differently. We assume some diffusion policy. Let's again go with Basel, for instance, right? And then we're going to introduce 2 auxiliary losses that allow us to leverage the entire space of our data instead of just the language label part. And mostly thanks to the contrastive latent alignment that we do. And I'm going to motivate this now in the next very few slides. So, and we can just like already to show, I don't know what happened here, but we can also show that we basically outperform our baselines again on various benchmarks here. So like just to give you an idea that most of the time, if we actually use like language encoding, right, we have something like a clip encoder or something, anything like this, right? Or Voltron, and those are great, but they're basically trained a priori, right? And then basically people just use them, right? So we basically use this language encoders and then try to fit our policy on there. But we argue that why would we stop with this, like including language or leveraging this symmetry between, let's say, scene and language in the encoder state already, right? So where we actually want to have this alignment is in the policy space, right? Because that's the most crucial space for our behavior, right? In the policy latent space. So what we're doing is that we're introducing in our, like, so we're still using a clip or Voltron encoder. We also have ResNet, actually like completely backpropagated ResNet encoders here also. But we introduced 2 auxiliary objectives, right? The first one being the progressive latent alignment in order to deal with this sparsity of language annotations. So how does this work? If you imagine that you have like a trajectory, right, like some demonstrations and some task description or some goal, like stack the blocks, right? So then we have like at this point, the blocks are stacked, right? So we have basically our goal image and our current state where we are right now. But at the same time, since we have an annotation here, we can also say that our goal would correspond to this language and our current state. And both of those, if we like encode them in some vector space and so on, right? They might be in our latent space of the policy, not actually that close to each other, right? Because the encoding resulting from this situation and the encoding resulting from that situation don't have to be close to each other. However, we want them to be close to each other because we want to drop in like or replace one for the other, right? So at the same time, if we have basically just the language label, right, we can also project it somewhere in our latent space, and we know this language label are different, right? So we want to push them away from each other. And this is basically what our latent alignment does. It restructures our latent space, or it has introduced an additional loss that encourages the proximity of scenarios where we actually have an image and a language description to it, and push it away from states that look different or have different language annotations. And the second auxiliary loss that we introduced is mass generative foresight. And the idea here is basically that we kind of want to train our policy space that it is able to foresee a little bit into the future, right? So if we have our current state, we actually want to predict these missing pieces or missing patches of some future state, or be able to predict it, right? So that our feature space, our latent space is representative enough or contains enough information in order to be able to do this task. So you might be wondering, why do we just do patches and not the entire image? We tried several variations, and this one worked by far much better. And our explanation for that is that if we try to reproduce always the entire image, we might also end up trying to reproduce parts of the state space or the image space that are not relevant for the actual task, right? Whereas here, this would like average out. And in fact, in the reinforcement learning community, people came to the same conclusion, that we only try to restore basically patch-wise instead the entire image in order to avoid distractors, or avoid producing distractors. And the evaluation here again, like works, or we can show that we, even with only 2% language annotation, we actually perform really, really well on the Kelvin benchmarks, right? ABCD in this case, so training on ABCD and performing on D, but also in our real world kitchen task, where we just like annotated or like asked the robot to do things in our toy kitchen. And this is a screenshot from this morning. So to this day, we're still second on the official benchmark, even though a lot of these work came out afterwards, right? And here also Robo Uniview, first of all, much more parameters, and second also privileged knowledge that we don't have, right? Like the CAM parameters and RGB data. And the same for the ABCD to D test. So this was D to D, training on the D dataset and testing on D dataset, and here training on the entire dataset and testing on D. And some interesting follow-up work on MDT, on the multimodal diffusion transformer, now from, I think, Hong Kong University, not 100% sure, but I believe that was Hong Kong University, where they actually now follow the same line of thought and like the same, or use actually our architecture, but with entire video predictions instead of just images, which also like seems to work really, really well. It's really exciting. Yeah. So again, this was published at RSS last year, so 2024 in Delft, which was really nice. And yeah, again, we basically current SOTA on these benchmarks. And as I mentioned, we actually even evaluated how low can we go, and only 2% of language annotated data still is sufficient in various like tasks like Libro and so on. And yeah, but you might argue, well, 2% sounds good, but somebody still has to do it, right? And yeah, so I guess you don't want to do it, right? So we were thinking like, how can we actually get this done even nicer, right? So how can we label observed robot behavior efficiently? And this time efficiently means with respect to the human labeling effort. So how can we reduce that part? And this is something that we presented last year in Munich at Coral. And the idea is that if we have like an actual unlabeled data set, like of state actions, of robot behavior, can we leverage current existing foundation models, right, in order to generate data? And all of you might be like, oh, well, Rudi, this is boring, right? Like you just use a VLM and then you put like images in there and then it tells you what it sees on the image and everything is good, right? Yeah, that was one of our baseline. It doesn't perform well at all, right? It's horrible. We made a much more structured approach where we used various VLMs or various like foundation models for different parts of this multi-stage approach here, right? So for the task generation, scene labeling, and the key state detection. And that basically outputs our label data set, which we then can use for training a language condition policy. And we do this all zero shot. So none of this part here is tuned or adapted in any way. So all of these models are as the weights are reported online. And the cool thing is, which is really nice, is that what this means is that if there's a new model coming out which performs better than the old one, we can just plug it in and directly run our system again and hopefully have even better performance. So since I'm already at 45 minutes, which is still 30 minutes less than I thought, I'm going to speed up a little bit, but generally the idea is that in the first stage, what we do is just like object retrieval. So we ask like the models like, which objects do you see in there, right? Like and so on, and then it gives us some output. And we use this then in a structured prompt to identify several features, like for instance the bounding boxes. But also we use a foundation model to predict depth from 2D images, right? We detect the gripper position and like eliminate it, like remove it. We predict the directional movement of the objects. So a bunch of like heuristics, a bunch of things that we try to get out of this scene once we know which objects are in there. And then we use those features to identify which key states are in this long horizon task, right? Like, so what were the individual relevant points in here, and use those then to generate the key states and the corresponding language labels. And this performs really, really well. Right, so we have like some examples here, and there's something to this method that I haven't talked about, but I just briefly want to mention, and that is that we can actually control the granularity. So we can actually decide how detailed this description should be, right? So like we can just make sushi, or we can be like, go over to the rice bowl, like roll out the rice, pick some fish. I don't know how to make sushi, obviously, but yeah, so we can control the granularity, and we also have like very, very diverse like natural labels or natural annotations, which is like actually a problem. So I'm going to talk about this in a second, but like our grounding accuracy is significantly higher than for just any individual model, right? And our policy overall performs very, very good and reasonable. Like one issue is that because our annotations are so complicated now, like or so natural, let's say, most models can actually deal with them. So we actually have an issue here now, right? So because the policies, as I said, if they just use like a clip encoding or something like this, then maybe the language is too diverse or can't be mapped properly in the latent space that they trained on, right? Because if you actually look at the language data, something that I didn't mention is that most of the data is either, or a lot of the language data is garbage, right? So because like you use some online service in order to label your data, and people figured out that, hey, as long as I put something in there, it's fine, right? So there's YouTube links actually in some of the, in the Bridge v2 data, for instance, there like just YouTube links to like Akon, It Doesn't Matter or something like this, the song is called, I don't know. Then you have like multilingual, like even within one sentence, multilingual descriptions. Yeah, so what can you do to prevent this? Other data sets, they use templated language. So they always say like, this is the task, fill in gap. What that results in is a very structured instructions, right? Which is fine for the encoders that you have, but if you have natural language as an instruction, it breaks down, right? So we had to do, in order to make this work, we had to dump down our language labels even. We had to prompt our method to be like more structured in its output. So what we need, so this is a call to action, right? So what we need is actual like policies or language conditioned behavior that can deal with this diverse natural way of communicating, right? So anyway, so this was presented at call last year, right? So if you're interested, please go ahead, take a picture. All the code, everything I talk about, all the code is online. Yeah. So we're almost there, right? So in order to do all of this, you might argue, okay, right, we need to increase some parameter size, right? You get more and more data, you have more complex language and so on. So that is a problem, right? So like how large can you actually go? And these days, a lot of SOTA policies are almost monopolized, right? So like there's 3 companies in the world that can run a lot of these policies, right? Like, and that's it. So one of the questions that I have, or one of the questions is like, how can we actually achieve SOTA performance and scale with data efficiently, right? And efficiently here means in terms of parameter space, but also in compute cost. And to make it very fast, like since this is still work under review, we introduced MODE, which is short for Efficient Mixture of Denoising Diffusion Policies. And here the idea is that we actually have multiple, that we introduce a mixture of expert into our denoising process, right? Where we have different expert hats and then that are responsible for different noise scales in the diffusion process. And what this allows us to do is much, much more parameter efficient. So, I mean, this would just be like a zoomed in view of this part here, right? Where we basically say our noise conditioning tells us or inserts noise into the different experts, and the gating tells us which experts are actually relevant. We do some additional things like caching in order to be even more efficient during inference time, but we evaluated without caching. So some analysis here. If we actually look at the experts, you can see that there seems to be like some structure, right? That the different layers or different experts focus on different noise levels or cluster them even together, right? So that we could actually use a caching or a mixture between those different experts in order to speed things up even further. But you see some experts feel more responsible for higher noise levels and others for lower noise levels. And what this means in terms of like our promise of parameter efficiency and these kind of things, right? We scale much better with higher batch sizes, right? Maintaining significantly fewer flops, right? So this would be with caching and without caching.
I guess you also compared this to like just uniformly assigning the, like also having different models for different time steps, but kind of like splitting this in a uniform way?
The splitting is learned, right? So we don't like, no. I'm not actually sure if we did this.
Okay. Yeah, I would be interested in seeing that. Because I think for vision, people did like the unlearned splitting. Yeah. It would be interesting to see how well it like improves performance if you actually learn the allocation.
Okay. Yeah, interesting. No, I don't. We would have to ask Moritz about this if we did try it out. But like as it is presented here, it's learned. Like which experts care about which part, right? And then we actually said like, okay, great. So now actually let's show that it can scale with data. So we looked at the OpenX embodiment data set and decided to pre-train on some of the data, right? Like that is in there, like on a selection of data, right? And we trained it for 3 days on 6 A6000s because that's all we have. And we can see that we actually outperform, like here, for instance, in this case on a simpler benchmark, OpenVLA and Octo, which are significantly like larger, right? With like a fraction of the necessary pre-training or compute time, right? So this is like quite exciting results, and we're waiting for the feedback on this work, right? And then, yeah, some experimental results. Also, like we almost achieved like almost 100% performance, like 90 something, right, on the challenging long horizon 10 tasks. And of course, like here on Kelvin ABC, which is a zero shot task, right? So you train on ABC and evaluate it on D. With pre-training, we actually also get sort of performance here. And in fact, again, we are on like mode is the second under MDT on the ABCDD task, and here without proprioceptive information, we still perform highest top of the official benchmark. So some issues that mode has and similar policies, right? And that is that we need to scale up and up and up, and like even mode uses still a language encoder, right? And doesn't just like a clip encoder, right? There, like we would have similar issues with this natural language and so on, right? And the second thing that changed since over the last couple of years, we don't only have task agnostic single robot play data, but we also have robot agnostic data, right? With this OXE data set, we actually have like this cross embodiment data, right? And we try to ideally want to learn policies that are able to deal with all kind of different data, right? So how can we leverage the vast amounts of visual language data in robot agnostic behavior, right? You can see no efficient here. So like the thought originally was like, okay, if we just have a big enough diffusion transformer, right, and we just throw diverse data on top of it, then we're all good, right? But this doesn't really work well because what we're missing is still this visual language understanding that current VLMs have and the given encoders don't, right? So we somehow need to include VLMs in this process, right? Or we don't have to, but like it's a reasonable assumption, right? So it's a reasonable trajectory to follow. So the question now becomes, which VLM do we actually want for pre-training? And if you look at the current state of VLMs, you have like something like 7 billion parameters, 17 billion parameters, right? Like giant models, and like almost all of them have 2 billion plus. And if you followed like some hype earlier or late last year with Pi 0, or mid last year with Pi 0 and so on, they actually used polygamma and had good success with that, right? Combining this with diffusion approaches. And RoboVLM uses Cosmos 2, which has 2 billion parameters. But all of these are not actually usable for us, like if you're GPU poor as we are, right? So what else can we do? Well, we can go back to the question and add the efficiently. So we want to do this in an efficient way, right? And here in this case, again, efficient with respect to the amount of parameters and the compute costs. So luckily, or like really excitingly for us, there was a new VLM coming out recently, and that was the Florence VLM. So Florence has like 0.8 billion parameters, so it's very small from Microsoft, right? And in addition to that, it has a very, very nice architecture, right? So it has an encoder-decoder architecture, which allows us to basically just scratch the decoder part, insert some projection layers. I think we have a 3-layer MLP here, right? And then use some flow policy on top of that. And with this, actually, we can also go one step further and say like, oh, we're also gonna use different tokens for different action spaces, like for instance for bimanual robots and so on, but use the same latent policy on the or latent space, right, that we embedded in. And that outperforms even those giant models while only having, I don't think I mentioned it, 0.6 billion parameters, plus something for the policy, but like barely anything, right? And we also solve Calvin ABC, which is the zero-shot task, with almost 100%. Yeah, and the TRI benchmark is hopefully the new one that we can excitingly try our stuff out on instead of the Calvin benchmark, which becomes a bit soft these days. And yeah, so we actually can also show this that without ever having trained in these lighting conditions, and you could argue that like these lighting conditions should make it very difficult for a policy, right? Without ever having trained in this darkness, the robot performs completely fine, right? The same goes if we now add distractors or more objects into the scene that we never had, right? And even if we are now changing the policy or the tasks in language commands and in vision to objects that have never been seen before in the demonstration, in the actual fine-tuned task, right? So yeah, and with that, the very last slide, or slides, something that we haven't addressed yet is how we can collect human data in various domains efficiently. And this is something where we had a study last year on what would be the best way of collecting these data using virtual reality, right? Like if you use a robot or a controller and so on. So I encourage you to look into this work if you're interested. But the coolest thing is we, of course, continued. We looked into what is out there and said none of those data collection frameworks is actually sufficient. So we presented one that can address all of these tasks. And we can now, like in the system, track your hand. Like we have gaze tracking in there. Motion controls are supported with the Meta Quest. We have hand tracking and voice tracking. And we already implemented in this framework common benchmarks like MetaWorld, Libero, RoboCalsaf, NCGM, Orbit, Arnold. For Genesis, for this simulator, there so far exists no benchmark, but as soon as it does, we can also include it in here. So if you actually want to feel like your robot in one of those benchmarks, like that software will, or that framework will help you. What does this actually look like? So for instance, an idea here would be that the student now is manipulating things in augmented reality. So the student sees partially the real world and partially the virtual world, right? And for some of the cups, the cups are just virtual, but the robot that the human is actually, or the student actually is manipulating is the real robot, right? In this case. And we can also do this with multiple performers, right? So we have like collective data collection, which is really, really nice. And we can also do fun things like table tents in the office without having to explain why we bought a table tents board. Yeah. against the robot, I should say. Okay, with this, 68 minutes, right? I'll thank you all for your attention, and our